Hello, my name is Manish Patra and I'm gonna explaining this temperature composition curve. Okay, so temperature composition curve is basically a relation between the temperature and the composition of a mixture of liquids. Okay, so under temperature composition curve, under temperature composition curve, it is basically of two types. Two types as if one curve comes under ideal solution and two curve comes under non-ideal solutions. Okay, and we know this thing that under non-ideal solution there are two main cases. One is positive deviation and the other is negative deviation. So basically we have three curves. Okay, basically we have how much? Three curves. Now, for ideal solution, we know ideal solution is a solution that obeys Raoult's law. Solution that obeys Raoult's law. And from our junior classes, we know the graph of ideal solution will be like this. This is the graph. Here, if we consider only pure component of A, which have x equal to 1, then I can plot the vapor pressure of it as P naught A over here, and for B I can put here P naught B. Okay, and we also know that temperature and vapor pressure are inversely related, or you can also say that boiling point and vapor pressure are inversely related. So here the pressure of A is greater than the pressure of B. I mean the vapor pressure of A is greater than the vapor pressure of B. So if the vapor pressure of A is greater than vapor pressure of B, so the boiling point of A should be less than the boiling point of B. Okay. So here we can see here the temperature of A is lowered and the temperature of B is higher. Okay. And this type of graph will form. Okay. Okay, I'm explaining this curve over here, explaining this graph in detail. And after explaining this graph, the two other graphs will be very easy to understand. Okay. So what we discuss just now, that is temperature of A is less than the temperature of B, because the pressure of A is greater than the pressure of B. I mean the vapor pressure. Okay. Now let us consider a point C where the liquid mixture have its boiling point. Okay, I can show it like this. Okay, it is already given. Now if I ask you that what will be the composition of liquid phase and what will be the composition of vapor phase, to uh, find the composition of vapor phase and the composition of liquid phase, we have to draw this upward curve and lower curve or downward curve. Okay, just a second. This is the upward curve and this is the downward curve. This upward curve basically represents the vapor phase and this downward curves basically represents the liquid phase. Now if C is considered as the boiling point of this mixture, okay, so the composition of this mixture in the vapor phase and in the liquid phase at this temperature, let this temperature be T1, at this temperature will be how much? Will be this. Okay, here we have to take one point and over here we have to take one point. Now see the composition, we can easily see it over here, over here. Now let the composition in the vapor phase at this position, I mean at this temperature, is xa equal to 80% or 0.8, or xb equal to 20%, or we can also say it as 0.1, sorry, 0.2, because we know this relation, that is xa plus xb equal to 1. If xa equal to 0.8, this should be 0.2. Okay. Okay, now see what happens. Above this vapor phase, only one phase is seen, that is the vapor phase. Okay, this part is only vapor phase, and below this only liquid phase is seen. Basically what happening here is that this vapor and liquid phase are in equilibrium. This thing is in equilibrium, this thing is in equilibrium. Okay, now what will be inside this curve? And this curve is a length shaped curve. I'm writing it here, length shaped curve. Inside this length shaped curve, both liquid and vapor phase will coexist. So this is what we have to know. Okay, I have written all this thing over here, that vapor plus liquid coexist in this curve, and this is the vapor phase. This curve is the vapor phase, and this curve is for the liquid phase. Above the vapor phase is above this vapor phase line, only the vapor phase is seen, and below this liquid phase line only the liquid phase is seen. Okay, now see, I have already discussed this. That means the point on the red line, yeah, the point on the red line, that is this point, shows the boiling point of the mixture. Okay, now the composition at this temperature T1 in vapor phase is uh, xa, or you can also say it chi a equal to 80%, or this is 0.8, chi b equal to 20%, or we can also say that as 0.2. For chi a it is 20%, yeah. For here it is 20%, and these values are just assumed. Okay, these values are completely assumed value, these are hypothetical values. I'm just taking it, this is 0.8. Okay, 0.2, this is 0.8. Now component which should present in distillate, which component should be present in the distillate? Now again I am coming to the curve. Here I can see Ta is present, here is Tb is present. If Ta is less than Tb, that means vapor pressure of A is greater than vapor pressure of B. So that again mean that the vapor pressure of A, which is greater than the vapor pressure of B, will evaporate faster. Okay, and it will get condensed by a condenser into the conical flux or the distillate. Actually this is the distillate, and here the liquid is present, here the mixture is present, and the mixture is of liquid A plus B. Okay, now this thing have lower vapor pressure, and this component has higher vapor pressure, so this will evaporate faster, and this will come here. So I can say that is basically liquid A. And if I ask that component that is present in round bottom flux, this is nothing but that liquid B, and yeah, but it is not pure B. Okay, it has some amount of liquid A, but the maximum proportion is B. I'm explaining this thing again. Okay, now see, here I have already marked that this is the composition of the liquid phase. Now if I increase the temperature, so let us increase the temperature. Okay, so I'm increase the temperature to here. Now see what will happen if I increase the temperature to here. Okay, So firstly draw a line on the left side, then on the then on the right side. See, when I've increased the temperature to T2, let here I can see in the liquid phase the composition of liquid is coming somewhere around 0.1 XA and XB is 0.9. So what we can observe is basically when we do repeated distillation, we can see the composition of liquid B is increasing. Okay, the component liquid B is increasing in the round bottom flask. Okay, that means how can I track that? By this mole fraction that we can see right now. Okay, so inside lens shaped curve we can see liquid and vapor coexist. Above vapor phase curve and below the liquid phase curve, one phase is seen. Okay, now here the mixture is given, the vapor pressure of A is greater, so it will evaporate faster and it will cool down over here, and as the vapor pressure of B is less than A, it will remain here, though it is not a pure form, some of the component of A will also be here. Okay, that we saw here. So we can write this thing also. Let this point be, I mean, okay, let this point be what I may call it uh, A1 and this point as AB, sorry, A2. So what I can write here that A1 is more richer in A and A2 is more richer in B. By repeated distillation, this A2 will become again more richer in B. Okay. Now for ideal solutions, for positive deviation, we know this thing that P total must be greater than PA plus PB, and this is the curve that we know from our junior classes. And at this point we can see maximum vapor pressure of solution is seen. Okay, at this point. Okay. Okay, so the corresponding temperature versus chi graph will be how much? It will be what? It will look like this. Here we can see the vapor pressure of A is greater than the vapor pressure of B. So here the boiling point of A is definitely lesser than the boiling point of B or the temperature of B. Okay, now here what we are observing is that here maximum vapor pressure of the solution comes. Okay, so here minimum temperature is coming at this position, at C position. Okay. Okay, now over here this is very common, that is xa equal to 1, xb equal to 0, and xb is increasing in this way and xa is increasing in this way. Okay, I'm not showing that. So okay, here what we have to do, here we have to deal this left side and this right side separately. Okay, so the first thing that comes in our mind, that here the temperature composition curve is continuous or not continuous. Definitely we can see that here the temperature composition curve is actually not continuous. This is not continuous, and for the previous graph it was continuous. Yeah, so now we will do some curve reading. Curve reading means now we will analyze this curve, how this thing is happening. Okay, suppose I'm boiling the liquid mixture of X composition. At that same time the vapor composition is X1. Okay, over here when the liquid when the liquid mixture have a boiling point of suppose T1. Okay, the liquid phase have a composition of for example, what may I say, For it will have such a composition that will be richer in A, and at the corresponding vapor phase it will have X1 composition which is richer in C, that we can see here, which is richer in C and this is richer in A. Gradually after repeating this here distillation, we can see that uh, this X composition will shift more to the A side, and gradually we can obtain the pure A. Okay, and in the distillate we will see this C thing, this C. Okay, now see at C what is special about C. But before that I'm coming here. Okay, suppose I'm boiling the liquid mixture X composition, yeah. At the same time, the vapor composition is X1, which is the distillate. After some time, we will see that the residual liquid composition will shift towards A, and the vapor phase composition will shift towards C. And this C is known as minimum boiling azeotrope. Actually, in C, azeotropic, the C is known as azeotropic mixture. The composition in C is known as azeotropic mixture. Okay. For example, here the composition is Xa equal to 60% and Xb equal to 40%, and this thing is known as azeotropic mixture. Azeotropic mixture, and this is the very special condition where we can see both this liquid will boil at the same temperature. Okay. So at this, actually see, fractional distillation is only applicable if the boiling points are different. If the boiling points are very close to each other, then also we will surely can do fractional distillation. But if the boiling point is same, if it's boiled at a constant temperature, then we cannot separate that thing, that mixture. So yeah, residual liquid composition will shift towards A and vapor phase composition will shift towards C by repeated distillation. Okay, this thing happens by repeated distillation. Now see, distillate is richer in C, that is that X1. Okay, X1 will gradually move towards C and it will be richer in C, and residual liquid will be richer in A. Now in this way we can obtain pure liquid A. Where we can obtain this pure liquid A? Where we can obtain this in the round bottom flux. And after obtaining this liquid we have to collect this thing out. Okay, we have to take this thing out. Yeah, but it is not possible to obtain pure liquid B. Yeah, now see the right hand side. When Y composition of liquid mixture is heated, the corresponding vapor phase will have Y1 composition. Let us see the right hand side. For example, suppose this is Y and this corresponding vapor phase will have Y1 composition. Here what we can see, here by repeated distillation we can see that this Y will shift towards this side and this Y1 will shift towards C side. So here the vapor phase will again be richer. Here the vapor phase, that is the Y1 composition wala phase, will shift towards C side, and this Y composition, that means the liquid phase composition Y will gradually shift towards B side. That means this Y will be richer in B and this Y1 will be richer in C. And by continuous or by repeated fractional distillation, time will come that this thing will happen like this, and yeah, so this pure Y we can collect. Okay, pure Y mean pure B we can collect. So what is written here, when Y composition of liquid mixture is heated, the corresponding vapor phase will have Y1 composition. Gradually by repeating the distillation, Y component shift to B, and then in the round bottom flux B is obtained. B is obtained. And Y1 composition of vapor phase will shift towards C. And here the residual liquid is what? It is B. Will be present in the round bottom flux and it will be richer in B. Definitely, actually it should be richer in B because it is a pure one. And distillate will be richer in C. Yeah, and this comes from the vapor phase. Now see the azeotrope that we were observing there. The composition was that I have taken is 60% and xb is 40%, or you can also say that as 0. 0.6 and this is 0.4, and the C point is known as azeotropic mixture. Okay, this thing is azeotropic. Okay, but the liquid and vapor phase has the same composition. Okay, here note one thing. Here I am saying the liquid and the vapor phase has the same composition, but the liquid, but inside the liquid, the two components may not have the same composition. Okay, here I have also shown that. Here I have shown that the uh, component A, the mole fraction of component A, we have will be 60%, and the component of uh, B, component B of liquid will have 40%. Yeah. Now let us assume one thing. Here the mixture, the azeotropic mixture I have taken, and I've taken it in a 6 is to 4 ratio, or you can also say that as 60% is to 40% ratio of A and B. Is the same thing. Okay. Now if we heat this thing, two thing can happen. Okay. If we heat this thing, then one thing happen. That means all of this liquid will evaporate on spot. All of this will get evaporated on spot. Okay, now if we cool this thing, again a liquid phase comes on spot. Liquid phase comes on spot. Okay, now for negative deviation, basically negative deviation, uh, the detailing of the negative deviation we know from our junior classes. That means the curve will look like this, and here will be the minimum vapor pressure, and for this minimum vapor pressure it will have the maximum boiling point over here. Okay, one thing here, it is achieved, this azeotropic mixture is achieved at a minimum boiling point, so we can also say that as minimum boiling azeotrop. Minimum boiling azeotrop. So yeah. Okay, and here the vapor pressure of A is greater than the vapor pressure of B, so here Ta is lesser than Tb. The concept is basically the same as the previous one. Okay. Okay, here also the same thing gonna happen. Let us take this point. So this thing will come gradually, this side will shift to D side, that means achieving a azeotropic concentration, and this azeotropic mixture will be known as maximum boiling azeotrop because its temperature is higher. Maximum boiling azeotrop. And here also we will get pure A and pure B. Okay, and here also we have to consider this left and right side separately. The basic is same as that of the previous one. Okay, so that's it. Thanks.